right, next up we have area of a parallelogram formula. So now we've kind of played around on the floor a little bit. We're thinking about maybe I'll start crawling a little bit here. Crawling with some of these area formulas here in terms of seeing where they're coming from. The area of a parallelogram equals the product of its base times height. Where to remember that? Well, that's the same exact freaking formula to rectangles, which we just proved in the last video. Now, is that a good video? Yes, it was. That was a great video here. So thank you for watching that here. A equals base times by height, okay? Remember, these two are measurements, right? Measurements of one dimension, okay? Base, right? We all know what a base of a parallelogram is, right? Bases of a parallelogram are parallel to each other, right? Definition of parallelogram here. The key thing about remembering this one is going to be the height, okay? So what the height means here, height, and this is why I really impressed upon you this thing last class here. Height represents the altitude. Okay, altitude between the bases, okay? So that is the perpendicular segments connecting the two bases. It's not a side, okay? It's not a side of the shape. H is not a side of the shape. H is the height, and that is the altitude. That is the altitude here. So this is what we're going to prove, okay? And let's go ahead and do that now. What do you think it's going to improve? Well, it's going to improve what we just proved right before this, which is going to be rectangles, right? So we are going to use the whole rectangle theorem, right? That a rectangle's area equals the product of its base to its height, okay? And its height actually would be a side length. Yes, it would if it were a rectangle, because the rectangle and rectangular sides, the consecutive sides are perpendicular. So anyways, let's do it. Let's see where this freaking formula comes from. Let's go ahead and do it right here. I'm going to go ahead and get myself a nice little parallelogram. Go ahead and draw it in, okay? I think we can all agree. Right, these horizontal tick marks here gonna be parallel to these horizontal tick marks here. So these look parallel, and then what did I do? I went 2 over and up 3. Okay, there we go. Parallelogram. Nothing particular fancy about this one. Nothing particularly noteworthy. I don't want to just draw a rhombus or something like that, or a square, or a rectangle. I don't want to draw a particularly special parallelogram. I want a generic generic parallelogram, so I can prove this theorem, okay? So the key thing about this, about the dimensions, is I'm gonna mark this. This is B. Remember, lowercase for side lengths for the one-dimensional things here. So here's the left-right dimension here, it's base. This base length here times by the height, okay, times by the height. And the height here I'll do in green, because I've been doing that in green all along. Okay, so you might be wondering, what's a height of a parallelogram? Well, that is the distance in between the lines containing the bases, okay? So I can get a parallelogram's height this way. Okay, there's my height, base times by height, that product, the base length times by the length of the height, right? The length of the height here. I can even get it this way. Yes, I can. Yes, I can. Here is H right here, okay? Because this is perpendicular. This is from one base to perpendicular to the line containing the base, not the base itself, right? This is the base itself here, but this is the line containing that base. That's marked B here. Okay, so any of those would work. This would work. This would work. We can see it's 3 based on the way that this diagram is drawn out, but what if we didn't know? Ooh, we'll never know. We'll never know. We'll know. We'll prove it. We'll prove it, okay? The key to this, I want to prove that that base times by the height is the area to this parallelogram here. Here's how I do it, okay? Here's how I do it. Check this out. This is what I'm going to do. I'm going to introduce a parallelogram, okay? A parallelogram, no, sorry, a rectangle. A rectangle. I'm going to introduce a rectangle that has the same base here. Okay, but it's going to be a rectangle for my friends. And rectangles are what, right? Rectangles are, well, they're parallelograms, but they have 4 right angles. So if I have a rectangle with a base of B, okay, and a height of H, perpendicular here, I'm talking about this altitude of the original parallelogram here, I can build a rectangle like this that very convincingly has the area of B times by H. Okay, I'm going to refer to this, what we have in pink here, as region number 1. Okay, region number, I have an I there, I'm going to put a 1. I'm not using Roman numerals here, okay? Not Roman numerals here. So the area of rectangle 1 by the formula that I just proved with you last video, by the formula of how you prove the areas of rectangles here, it equals base times by height, the same base times by height as that freaking parallelogram has. And that's what I want to prove that these areas have got to be the same. Area of rectangle equals base times by height. And, okay, something interesting about this, okay? We got something called the area addition postulate here, okay? So the interesting thing here is that the area of the rectangle equals base times by height. The area of, this is going to get messy, okay, equals, okay? Another way we can think about the area of this rectangle is this, right here. Okay, right there is this. I want to call this region 2. Okay, I want to call this region 2. We can think of this area of the rectangle equals base times by height. Okay, area of region 2 is everything except for that rectangle right here. Okay, this triangle that's up here. Okay, so I got here area of 2. Okay, and plus. All right, let's see what we got here. Plus, this is a messier one. This is definitely a messier one right here. Area of 2. So here it's kind of like this trapezoid type thing here. We can say that 2 plus, here we have a right triangle up here plus the area, okay, area of 2 plus the area of 1, okay, equals, right, equals, wait. What am I telling everyone? Area of 2 plus area of 3, okay, I want to make this region 3 here. Okay, by the area addition postulate. Again, I'm not even really covering that with you, but you get the idea. Part plus part equals whole, or I'm talking about the rectangle right now. What is he talking about? What is this here? Okay, area of 2 plus area of 3. Okay, that would equal this rectangle here, right? Area of 1, which you already know is BH, okay? That equals BH. Okay, remember, this is 2 right here, okay? Okay, it equals the area of the rectangle, and the area of the rectangle equals BH. Right, equals the 1, right? The 1 was the rectangle here. So whatever, I'm calling that area of the rectangle. Okay, equals BH. Okay, so here's sort of that, right? This is my trapezoid. This is my right triangle. Okay, and what's interesting about this here, okay? Check this out for a second. I have this little region over here. I'm going to switch back to black, right? I'm going to switch back to black because I want to start talking about the area of the freaking parallelogram here. That's the whole thing what I'm trying to prove. And guys, man, proofs are confusing. They're hard to get there, but we want to justify it here. That makes for a great mathematician there, okay? So area of parallelogram. Okay, area of this parallelogram here in black, okay, equals what? How can I actually represent this through the area addition postulate here, based on what I have right here? Well, I got here area of 2. Okay, so remember the rectangle here that has base of B and height of H, so its area is BH, based on the formula that we had previously. Okay, that's 2 plus 3. Okay, that's 2 plus 3. What's the area of the parallelogram? We don't have the formula yet. This is what we are trying to prove right now, that it also has to be B times BH. We're trying to prove this theorem must be true, okay? Well, area of the parallelogram here, what we do know through postulate, through the area addition postulate, is that it's also this 2 section, this trapezoid here, right? This trapezoid here, this shape number 2 that I've sort of identified onto this drawing here, okay? Right, it's the trapezoid, but it's also plus this triangle over here, okay? This triangle over here. And I'm gonna mark that triangle, and maybe I'll get away from green because I already have green on this freaking diagram here. I don't have brown yet though, yeah, okay? Brown, I'm gonna mark this triangle 4. Okay, I got this here, triangle 4. So the parallelogram here is this purple kind of trapezoid with this little triangle on the right side there. Wait a second, what's the relationship between that triangle and that triangle over there? Well, think about that for a second. Hold on a second. So 2 plus 4, okay? Area of 4, area of 2, add them together, that equals the area of the parallelogram. So when you think about the area of the parallelogram here, as we work our way to getting to this formula, okay? Area of 4, well, that is a different right triangle, okay? So it's technically a different right triangle, but what do we know about it? Well, here, let me redraw this down below what I have here. Okay, so remember, I have the original parallelogram. What is it here? 1, 2, 3, 4, 5, 6, 7. Okay, so I just want to show it the way that you're seeing it again here. 1, 2, 3, 4, 5, 6, 7. Okay, up 2, 3. There we go here. I have the original parallelogram. Okay, and messy. There we go. That's good here. Okay, original parallelogram is made up of, this is set portion number 2. This is portion number, this is portion number 4, as I indicated in this diagram here, okay? I called 1 the whole rectangle, okay? I called 1 the whole rectangle. But if I introduce that rectangle I'm talking about, which is the sum of region 2 and region 3, as I put down here in blue, okay? Check out what happens. Check out what I can prove, okay? I introduce through a point outside of a line, I can draw at least one perpendicular through this here, okay? I can go up h in terms of length, okay? I can introduce another perpendicular right here, okay? So here is where my rectangle is right here, okay? I know that because this is a rectangle, what type of a triangle is this in a triangle angle of triangle 4? They're both right triangles, okay? So there are a few things that I'm going to prove for you right now. We do use this earlier proof stuff to get to this formula. That's why we need to learn proof so much for a semester. But triangle 3 and triangle 4 are both right triangles. A very important observation as we are trying to get to our proof here, okay? Angle 3 and angle 4 are both right triangles. What else do we know about this particular diagram? Well, we know that here, right? Regions 2 plus 4, that was the original parallelogram, right? That we're trying to improve is b times by h, which will be the same as the rectangle that you can offset. You can change back it, right? Remember, parallelogram is just a rectangle slanted over, right? It's offset a little bit here, okay? So we know that these here, the hypotenuse, so triangle 3 and triangle 4 are both right triangles whose hypotenuses are congruent because opposite sides of a parallelogram are congruent to one another, right? We had that theorem. Everything connects. Everything builds on itself. That's what this is all about, this course here, about getting there logic-wise. And I want to get there, even though I'm not requiring you watch this one here, okay? So we know they're both right triangles, okay? If I toss that rectangle there, if I move the parallelogram back to being a rectangle, kept that distance the same, there, base times by height. There we go. I'd have a right triangle here. I have a right triangle there. Ooh, the hypotenuses are congruent. You think we can prove those two triangles are congruent? Yes, we can. Yes, we can. Well, why? Well, we introduced a rectangle right here. This fits the definition of a rectangle now. We have opposite sides are parallel. Opposite sides are parallel here because we have all right angles here, okay? So we know that these two sides are also congruent, okay? These two sides are also congruent. Whose hypotenuse is congruent because opposite sides of parallelogram are congruent. Yep. And one leg is congruent. Okay? And another way we can justify that leg and that leg are congruent is because points on one of two parallel lines are always equidistant from the other parallel line. Okay? The other parallel line here. Okay? So that's congruent to that. That leg's congruent to that. They're both right triangles. What theorem can we use? Okay? The two, so therefore, right, we can do therefore, what I can say here is that area of shape 3 that I have in this diagram here equals area of shape 4, okay? Because the triangles are congruent, right? Therefore, triangle 3 congruent to triangle 4 by HL, okay, by HL. So in your textbook, like I'm skipping over this here, but it should make complete logical sense. If I know that that triangle is congruent to that triangle, then I know they would have to have the same area. So that's called the area congruence postulate, okay? Which would, if you look at the textbook, would go into justifying why this is a true, okay? So let's look back here. I know this triangle and that triangle, they're congruent to one another through HL. They have to have the same area. So check it out here. 2 plus 4 would have to equal the same thing as 2 plus 3. And what do we know about 2 plus 3? Okay, what do we know about 2 plus 3? Well, we know that the area of 2 plus 3, it equals the area of the rectangle, the way we could prove it using the other theorem here. So what do we know about the area of a parallelogram? Well, it also equals 2 plus, and using substitution, 3, okay? 2 plus 3, it's the same area as that rectangle that will get formed. So area of a parallelogram is base times by height. And there it is, my friends. We're now up and walking and crawling. We didn't have to go through it through class. You didn't have to sit through that during a lecture and fall asleep on your desks. Hey, we got there. Hooray. Okay, there it is, folks. Area of a parallelogram is the product of its base length times by its altitude. Remember, the altitude is simply the distance between those bases, the base that you're using for your calculation, okay? Because remember, on this here, those would also be bases. These two sides would also be bases of a parallelogram here, okay? So to get the altitude here, it would actually, altitudes oftentimes are outside of the parallelogram here. I could maybe get an altitude here. Nope, I can't get it to, I can't actually, maybe I can draw an altitude right here. Nope, it's not a right angle here. So anyways, you can get the area using these sides too. You just need to know what the altitude's like, the height is here, okay? And that is the distance. And distance, as we know, is the perpendicular segments that connects two different things, okay? Thank you guys for watching, and we'll wrap this one up, at least our first segment of these, with the area of a triangle formula coming at you next. Bye.